ESMLE application, or large physics code, such as the hardware hybrid accelerated cosmology code, CANDLE, which looks at drug cancer cell interactions, or even large-scale exascale instruments such as the LCLS2. You can think of it as a giant X-ray-based microscope used to look at chips and other very, very small molecular structures. Regardless what systems we have, they're producing 200 terabytes of data, for instance, 20 petabytes of storage per a trillion particle run, a petabyte of information to analyze one drug tumor interaction, or 250 gigabytes per second of data streaming off of a high-powered X-ray device. And when we compare this to the supercomputers that we have broadly available, we notice that there's a gap between the amount of storage that's available in total on these machines, the peak bandwidth that we have available to these storage media, and the total amount of memory that can be used in the short term on these systems. Now, the big problem is that even if we were able to get this, we'd have a problem. But you almost never get this. You almost always get some tiny fraction of the available data bandwidth or storage capacity on the system because you're sharing it with other users. There's a paper from 2015 which says that most even petascale applications get a fraction of the bandwidth that's available, on the order of 0.1%. So we need something to address the ever-growing volumes of data that scientific applications and instruments consume, while at the same time allowing us to do meaningful work. John, can you close the external door, please? If we're looking at applications, applications all across the spectrum are beginning to consider the use of lossy compression in their analysis, whether it's climate codes, the instruments that I mentioned, things that analyze the results of these large-scale instruments, traditional plasmatic numeric physics codes, quantum chemistry applications. They use lossy compression in a variety of different ways and to accomplish meaningful science. But today, as it stands, lossy compression is not approachable. There are too many interfaces, much like, for example, MPI, the message passing interface, had for networking before it was standardized. This makes using compression very, very difficult. It makes it difficult to configure, difficult to optimize. Users have very few tools in order to understand the impacts of error-bounded lossy compression on their applications. And my work aims to address this by providing a single interface to use, configure, optimize, and understand the effects of lossy data compression on scientific data. I want to give an outline for the remainder of the talk. We're going to begin with some discussion of background on compression principles to kind of catch everybody up to speed who may not be as familiar with the area. Then we'll proceed to a series of papers that I've worked on over the course of my dissertation relating to automatic parallelization, automatic configuration of compression, and understanding its effects. So what we see here are two pictures of Lake Hartwell, which is near Clemson. On the left, we have a losslessly compressed image. On the right, we have a lossily compressed image. You can probably tell that the picture on the right is still a lake, even though you can also tell that the quality has been degraded. The picture on the right is 17 times smaller than the picture on the left, which kind of gives you an intuition as to why we might want to use something like this. But if we look at quality metrics that scientists use to understand how well information is preserved, it actually does quite poorly on this particular metric. What we'd like to do instead is get a quality which is above some acceptable threshold, for in this case, 0.9, but we're still getting something that's 5 times smaller than what the losslessly compressed data buffer is. We want to find trade-offs that give us both good quality and good compression. So now I'm going to briefly discuss a series of error-bounded lossy compressors that have been developed since 2016 that try to solve both of these problems simultaneously. So the first of these is the ESZ, error-bounded lossy compressor. That is not an acronym. SZ operates by predicting, in essence, using one of two prediction schemes, the data that will appear next in the stream of points that is being compressed. And by making predictions about what those points are, we can essentially discard the information for points that we can easily predict what it does. Now, what happens if our prediction is false? Well, if our prediction is false, we just store the data as it was and from the original stream. There's no harm in doing that. We store it as unpredictable data. We then quantize the predicted stream. Basically, that means we map it to the nearest integer. Then we perform a Huffman encoding, which basically recognizes repeated patterns within the data, extracting them and replacing them with a smaller representation before we feed it through a lossless compressor stage that will kind of do a final compression of the operation. SZ is something of a moving target, especially when you're looking at the concept of performance. There have been over 30 papers published on SZ and its related family of compressors since 2016. And SZ itself has over 27 parameters, and that list just keeps growing. Users don't have an intuition about how to configure SZ because there are so many implementations and so many parameters that you have to work with. It makes it very difficult to work with. Additionally, as Sheng and others continue to work and improve the performance of SZ, the runtime characteristics of the algorithm change as they make improvements, meaning that an optimization or a tuning that was good a few days ago or a few years ago may not necessarily reflect what the best state of the art would be on the next version of the compressor. ZFP, also not an acronym, is a transform-based compressor. This is using a different principle, which is in many ways more similar to what a JPEG does. Now, how does it work? Basically, instead of representing individual values within the image that you're considering, it kind of represents each value as a sum of patterns. And by kind of understanding things as a sum of patterns, these patterns can be stored much more concisely than the individual values that make up those patterns. ZFP as a compressor has been largely stable since 2016, but since 2016, there's been recent hardware accelerated versions for FPGAs and GPUs, and some of these require additional tuning. So one question that kind of remains for even using just ZFP is what hardware do you choose based off the context of the scientific application you have, how much data, which one is going to be the most effective on the data sets that you have. And then finally, a more recent addition to the air-mounted lossy compressor competition is MGARD, which stands for Multi-Grid Adaptation Reduction of Data. It operates off so-called multi-grid methods, which operate by performing so-called coarsenings of the data. So what's a coarsening? Basically, instead of looking at the data as a whole, you kind of divide the data into regions which share certain characteristics. And if there is not if you don't satisfy some threshold that represents the complexity of that region, you then refine again and then have progressively closer and closer representations where you need them. So instead of looking globally, you kind of recursively look into sections that need to be refined. Since MGARD was introduced in 2018, it's relatively unstable in terms of its interface. And one of the larger problems with MGARD currently is its performance. So if users want to adopt MGARD to take advantage of the unique error-preserving properties that it has, you need a consistent interface to meaningfully integrate it into an application. And you need some ways to accommodate some of the performance penalties that MGARD has just because it hasn't been optimized yet. So now that we've kind of gone through a basis of the compression principles, the next thing to consider is LibPressio, my solution to the proliferation of interfaces, and how can we provide meaningful performance in a generic way to a variety of compressors. So the first question we'll consider is, can we construct an efficient abstraction for lossy compression of scientific data? And when we look at a collection of attempts that came before, whether it's Audios2, Cbench Foresight, HDF5, NumCodex, LibArchive, ZChecker, or SCIL, we see that there are gaps in the kinds of abstractions which result in decreased performance. So for example, zchecker only supports dimensions up to 4. libarchive isn't aware of dimensionality at all. And ignoring the dimensionality and the shape of the data buffer that you're passing in can result in a compression ratio that's somewhere between 25 and 35% worse. If you ignore the data type and you treat all data as if it's the same type and you ignore floating point versus integral data, that can result in an 84 times worse compression ratio. If you require that your compressor algorithm use commands like the C system call system to spawn exterior processes to work on the data, that can result in compression that's 20% slower than some techniques use. And perhaps most important for the future is the ignoring of arbitrary configuration types that are needed for some compressors, such as CUDA streams to support GPUs, or MPI communicators for supporting complex multi-nodal apps and compressors. There also are things that affect your ability to be productive with the code that you write using this. So tools like introspection and third-party plugins can actually have meaningful impacts on the volume of code, as we'll see in a moment. This leads us to identify a series of gaps. First, that there isn't a unified, stable interface for compression. The interfaces used to configure compression are difficult to use generically, making it hard to write optimizers around them. And some of the compressors, such as SZ up till 2 weeks ago, as well as others, are not thread safe or parallel, meaning that in order to address these, we need something that will unify the many incompatible interfaces while being efficient and taking care to have the best possible performance. Oops, wrong button. So over the course of my dissertation, I developed a library called LibPressio that provides a common interface for compression. It handles loading the compressors, configuring them, compressing and decompressing, representing data, reporting errors that occur during the compression process, and computing metrics upon that data in an efficient way. This represents the totality of the code that you need to write in order to compress and decompress a particular buffer using SZ with LibPressio. If you wanted to change that code to using ZFP, you only have to change the code that's in the red boxes. And additionally, if you load the configuration from a file instead of from hard coding the parameters, you actually don't have to change the code at all. This is a pretty radical productivity improvement that allows you to write generic code that handles a variety of different compressors and compressor schemes very efficiently. LibPressio currently has a wide array of different tools and plugins that I've developed over the course of my dissertation, and largely these represents code that you don't have to write. You can be productive using LibPressio from day one. One of the key insights that I had in developing LibPressio is this concept that I call a meta compressor. So a meta compressor is not a compressor itself, but it models the interface of a compressor. It behaves like a compressor. But instead of being a compressor themselves, they provide services atop a compressor. These can be things like automatic configuration tools that when you give it a request to compress the data, it finds the optimal configuration to compress that data with. Pre or post processing runtimes that you might want to use to increase the compressibility of your data, or even parallel runtimes that will take your task and then spread it out over a cluster in order to efficiently work through a large volume of data. We'll talk specifically about auto configuration tools and parallel runtimes later in the presentation. So I will talk very briefly about developer productivity. Writing for multiple compressors is difficult for a variety of applications that I've looked at here, including things such as Audios 2, zchecker, HDF5 filter plugins. Across all of these different examples, creating them at feature parity with the ones that already exist, we were able to reduce the volume of code required to implement these components by 67%. In addition to reducing the volume of code required to implement these, they also gained support for all 26 plus compressors and meta compressors in LibPressio, in many cases adding additional functionality beyond the functionality that existed in the program to begin with. So to summarize this section of results, can we construct an efficient abstraction for lossy compression of scientific data? Yes, we can, and we save at least 50% of the volumes of lines of client code while reducing switching costs. We can also show that we have statistically insignificant overhead by eliminating the different kinds of concerns that I showed earlier in the presentation that come from ignoring the kinds of concerns that we identified explicitly in LibPressio. And all of this enables the science that we will see throughout the rest of this dissertation. Now we're going to move on to the question, what are the trade-offs between bespoke and black box parallel compressors? This work is in submission to IEEE transactions on parallel and distributed computing. So to motivate this problem, many compressors aren't currently leveraging parallel processors on the CPU, leaving some performance opportunities that exist. For example, SZ's bespoke parallel implementation only supports 3D blocks of IEEE 32-bit floating point numbers. ZFP doesn't parallelize decompression at all, and MGARD compresses neither compression or decompression. So the question that we have is, can we solve this problem generically with LibPressio without giving up as much of the performance benefits that we have from writing bespoke parallel compressors? So why is this difficult? One, naive solutions can make unneeded copies, which can result in a 10% performance penalty, depending on what size buffer you're looking at compressing. And up until 2 weeks ago, suppose that you wrote this code and it worked beautifully with ZFP, it would have crashed with SZ. And the reason for this is that up until 2 weeks ago, SZ wasn't thread safe. But because LibPressio provides enough information to the developer writing the plugin, they can determine whether or not the library is thread safe and make sure that there are certain protections. The other kind of open question is, will this provide sufficient benefit to actually matter? So in general, this is the approach that we took to performing automated parallelization. The picture at the top represents the compression scheme before we operated on it, and below represents the compression scheme after. So we have some region of data containing many values. We feed them all into the compressor. We receive the compressed stream. With our automated parallelization approach, we break the section of values into subarrays that are contiguous. So by doing so, we then feed each of these subarrays in parallel using OpenMP tasks to separate threads of a compressor. And then we get separate compressed streams for each compressed region. Once we have these, we write out a short header that describes the length of the compressed stream. And then we, in parallel, write out the data that corresponds to the entries from the compressed streams. So how does this impact performance? So when we look at LibPressio and automatic parallelization, we see that we have a slightly slower version than what SZ or ZFP have for their bespoke versions, but we're actually relatively close. Additionally, we work for compressors such as MGARD out of the box, which didn't natively have a concept of parallel compression. You may notice, if you're looking carefully at this figure, that the number of chunks equal 49 does not exist for MGARD. That is because MGARD does not allow subarrays to be compressed with a dimension with a value less than 3. So you can compress a 1D array that, as long as it's at least 3 long, a 2D array as long as it's at least 9 by, or it's bigger than 9 by 9 or 3 by 3, and a 3D array as long as it's bigger than 3 by 3 by 3. But this isn't true for chunk size equal 49 because we have something that's by 2. One of the other things that we observe is that the chunk size for this kind of approach really matters. So on the ideal chunk size for this particular problem, which is 14, we find that there's a 3 to 7% compression ratio penalty as a result of using a generic black box approach as opposed to a bespoke parallel implementation. So why does this happen? Well, when we're using a generic approach, we don't have access to whether or not there's repeated metadata structures that are being stored copies of in each of the different streams. So because we're not taking into account these metadata structures, we're ending up with duplicates which are penalizing our compression ratio. When we look at the decompression story, it's relatively similar. We have slightly slower performance for decompression for SZ, but we have successfully parallelized ZFP's decompression, which was previously not performed. And then we also parallelized decompression for MGARD. And again, even for ZFP, or excuse me, even for SZ, our scalability is relatively similar compared to what we had prior to our approach. So let's kind of summarize the results in this section. So what are the trade-offs between bespoke and black box? Tuned properly, you see about a 3 to 7% lower compression ratio, approximately 5% slower than a bespoke implementation. But we don't have to write code for every single parallel compressor. Additionally, because all of this conforms to the same LibPressio interface, users actually do not have to change their code in order to adopt parallel compression. It can be just a single configuration file change that they can then use and move forward. I mentioned tuning is an important problem when using parallel compression. And actually, tuning is the next topic that I will address in my research dissertation. So now we're going to turn our attention to automated configuration of compressors, beginning with my work, FRAS, which attempts to compress data to a fixed compression ratio. So what's our goal? Ultimately, users don't care about point-wise bounds on their applications, or at least most of them don't. What they want to bound is some quality metrics. So at the beginning of my talk, I mentioned the SSIM as an image quality metric. You might want to be able to bound the quality on the SSIM. Now, going directly from an error bound to something complex like an SSIM is kind of a big jump. So we're going to start with a slightly simpler problem of bounding the compression ratio. So in the process of trying to do this, why would you want or care about bounding the compression ratio? Well, this is actually one of the most common requests that teams have when they go to consider adopting compression. They're like, what's the best quality I can get for the available size that I have allocated to me? That's the problem of doing fixed ratio compression. In terms of prior work, there was one major prior work, which is ZFP's fixed rate mode. But an important thing to note about ZFP's fixed rate mode is that it's not error bounded. So if you care about the quality of your application and you want strong guarantees on the individual points, you're not going to get there using ZFP's fixed rate mode. Additionally, as I've discussed, not all problems have a problem structure that is best amenable to being preserved by a compressor such as ZFP. So in some cases, you want to use the kinds of compression principles in SZ or in MGARD, for example, that may work really well on your particular problem class. Additionally, we want this method to work with any compressor that comes up in the future. We don't know what the optimal design of a compressor will be in 10, 20 years, but we want to be able to write one set of code that will work and have longevity beyond the life of a single compressor. So the question we ask in this section is, can we tune the compression ratio by bounding can we bound the compression ratio using the parameters of the compressor, specifically the error bound? So why is this a hard problem? And I want to spend a little bit of time on this slide. So here we have kind of a preliminary result that we had from working on this paper, where we show the error bound set on the compressor against the compression ratio for a data set that we have. And what's kind of interesting to note here is that as we look at this curve, we see that it's not monotonic. So it's not consistently moving in the same direction, but it's actually relatively noisy. So even a relatively simple approach like binary search simply won't work, because the non-monotonicity of the problem makes this actually relatively difficult to solve. Additionally, the relationships between the error bound and the compression ratio, it's not something that we can easily express with an explicit formula. And because we can't express these relationships analytically, working with and estimating what the compression ratio will be for a given error bound is actually quite difficult. So what kinds of methods can we use? So I look to the domain of numerical optimization. And there are broadly three classes of optimization one can consider: derivative-based methods, including analytical methods and numeric methods, and then derivative-free optimization. Analytical methods largely won't work because, as I said, we don't have an explicit formula that describes the relationship between an air bound and the compression ratio that we're able to achieve. Additionally, numerical derivatives are often too slow on this particular class of problem. So what can we use? Derivative-free optimization, which kind of estimates the slope constructively by looking at points through each individual point as it comes up. So now that we're choosing to use optimization, we need to formulate our relationship between our air bound and our compression ratio as a function. So we formulate it as the max of some compression ratio Q over some air bound represented here by the vector C in some set of allowed air bounds. So basically we're going to consider air bounds up to 1 to the -4, for example. Then we have some set of data buffers which correspond to particular fields and time steps from a classical numeric simulation. And we have some function that allows us to take a uncompressed buffer and convert it into a compressed buffer. Most often, many compressors have some concept of an air-bound mode, so we take that into account here with theta C. So how do we then make this fast? We can parallelize this by field, running each field independently. We can parallelize by time step, by reusing the configurations that we find for prior time steps. And this actually works remarkably well. Over a set of 48 time steps for a climate application that we considered, we only had to retune sometime between 6 and 8 times for a particular field, meaning that we're not having to tune this operation very often. We can also perform additional parallelization by air-bound range. So what we do is we take the total range of lower bounds and upper bounds that we want to search, and we can subdivide it into multiple components that we will then search independently, stopping early if we find a solution. One thing you may notice from the graphic is that these regions slightly overlap. So why do we do this? We found during our evaluation that by slightly overlapping the regions, we were able to create sufficient what are called stationary points, these points that the optimization algorithm uses to identify which region to search next, to find points that are in the region that contains the overlap. So by overlapping slightly at approximately 10%, we find an optimal configuration. So how long does this take overall? And we found that tuning this process over an entire data set with many fields and time steps takes only 2 times longer than what an oracle that just knows the correct answer would take in the feasible case. So what do we here mean by feasible case? So if we look at these kind of points that I've circled now on the left, these are too small to be feasible. So why is that the case? Well, if we look at a compressor like SZ, its last stage is to run the data through a lossless compressor. And because it's running everything through a lossless compressor, we end up in a situation where we can't make the data larger than what the lossless compressor is going to natively shrink it to, which kind of results in an effective lower bound for how compressed or how low the compression ratio can be. Additionally, we can end up with regions between feasible compression ratios that can also occur, such as the region that I've circled here. So why does that happen? That happens because oftentimes as we search between different predictors in a compressor, such as with SZ, we have the Lorenzo predictor and the regression predictor. As we are switching between these being used over our data set, we end up with discontinuities in the compression ratio. So we have kind of a set of compression ratios that are moderate, then we switch predictors, and then we have a higher rate of compression until we switch again. And these trade-offs then introduce kind of these discontinuities, which make certain compression ratios that we might like to target infeasible. So to summarize results for this section, can we tune the compression ratio by bounding the error bound for the compressor? And the short answer is yes. And we have approximately 2 times overhead in the feasible case. We found that using new analytic derivatives was infeasible because you don't have an explicit relationship between the air bound and the compression ratio. Using numerical methods is too slow because we have to measure neighboring points in order to determine the tangents. We also found that consecutive time steps can often share configurations, meaning that you can drastically reduce the volume of tuning that you need to perform. Additionally, we found that some targets are not feasible because of properties specific to particular compressors. But there's a motivation for continued research here. One, compression ratio is a relatively simple metric, and users actually care about the quality of their metrics. They care about the image quality metrics that they use on a regular basis. They care about the statistical inference test p-values that they're computing upon their data. They want these kinds of results to be preserved, and they need tools to be able to do that. Additionally, compressors such as SZ have many parameters. Users want to be able to tune more than just an airbound. Additionally, the approach that we lay out in FRAS is too slow for some use cases. So we need performance benefits and improvements as well. After the publication of the FRAS work in IPDPS, the International Parallel and Distributed Processing Symposium, several other research teams looked at similar problems. They invented bespoke compressors for preserving the quality of a particular airbound, such as PSNR. They looked at trying to solve this problem for entire mathematically related families of functions using an approach called MGARD Q of I that I'll talk about in a little while. And they use systematic approaches, which look at a variety of different points systematically in order to find a solution that works. And we need to compare against these approaches as well. So now we turn to my work opzconfig that adapts the work that I did for FRAS into something that works in general for user-specified metrics that are suitably deterministic. So can we extend FRAS to bound simple user metrics and improve performance? To do this, we will begin with the formulation that we used for FRAS to define our optimization problem. We will then introduce a new term, which represents the fixed metric parameters. This would be like the weighting in a weighted mean, for example. We then redefine the compression ratio function Q as the user-provided airbound. We redefine C as the set of non-fixed compressor settings, those that we allow to vary over the course of our optimization. We redefine capital U the set as from the set of allowed airbounds to the set of feasible compressor settings. And then we redefine the compressor fixed parameters, the airbound mode to the compressor fixed parameters. What happens when we have constraints on multiple objectives? So what we can do is we can essentially define a piecewise function for our set of quality functions Qi and our set of thresholds on those metrics tau of I. We can construct a piecewise function that essentially penalizes whenever we've requested an airbound or requested a quality metric that doesn't, or an airbound that produces a quality metric that does not satisfy a threshold. So how does our approach compare against specialized compressors? And what we found is that while we are tuning, we're often not faster. But post-tuning, we're just as fast as what we would see if we were performing the compression. However, by using opzconfig to do this automated tuning process, we find that we're able to make different trade-offs than what specialized compressors are. Meaning that we can potentially reduce the amount of quality achieved while still remaining above the threshold that the user has specified, while achieving greater compression ratios. So by slightly lowering the quality, we can vastly improve the amount of data that we're able to compress. So just for a set of examples here from Hurricane and Miranda, we can see for some PSNR targets, we're able to see improvements as large as 201%, 114%, 320%. These are quite substantial improvements that would allow you to store a substantial larger volume of data. When we compare against FRAS, our previous work, we were able to use a set of optimizations to the algorithm in order to achieve a 56x combined speed up over all of the improvements that we made. To understand the impacts of each of the improvements we made, we did an ablation study where we looked at the three major things that we changed. One is the ability for the process to terminate between iterations by introducing additional communication flows in the algorithm. And we found that by doing this, we increased the performance of the operation from 3 to 15 times. When we look at the ability of applying threading within the compressor, we see an additional 2x performance improvement. And then some of the numerical optimization libraries allow multi-threaded searches. And by providing certain safeguards to ensure that this is done safely, we can additionally improve the search performance by 2x. In addition to all of the performance improvements we support arbitrary user-defined objectives that are sufficiently deterministic, multiple input parameters, and we allow extendable search methods. So as new search algorithms are developed that work better on these compression ratios, we can reuse the existing code that we have without having to change the framework. We can also, I keep on heading the wrong direction. So now I want to talk about the problem of MGARD Q of I. So MGARD Q of I stands for MGARD quantity of interest mode. So MGARD Q of I is probably the most mathematically heavy thing in this entire presentation. So please bear with me. MGARD Q of I has a notion of a Q, a quantity of interest, in a very similar way to what we have for opz config. However, MGARD places some additional constraints on their function Q. First, they require it be what's called a bounded linear functional. If you don't know what that means, basically that means that if you perform Q, you can treat it as if it obeys the distributive property. So this allows MGARD to make a series of assumptions that allow them to determine a scaling factor, gamma, that works for all problems of a particular family. So any problem that has roughly the same shape can have one scaling factor that takes a really long time to compute, but we can use this scaling factor on all new problems, and we can be mathematically guaranteed that we still preserve the error bound. The details of how exactly this is done can be found in the paper below. The important thing to remember is that the scaling factor is very expensive compute, on the order of days for problems that we would see at exascale, but it's provably reusable for all data buffers that we might want to feed into the compressor. Now, when we compare against MGARD Q of I, our method, when used with the SZ compressor, is much faster for one-off tasks, so that if we don't have this scaling factor, we are orders of days, if not weeks and months, faster than what MGARD is capable to achieve. For tasks that we are repeated or we already have the scaling factor, LibPressio opt, which may or may not have a valid tuning, is faster in 75% of the cases that we evaluated. Now, if we don't have to tune LibPressio opt and we can reuse an existing configuration that we happen to have, then we are on average 1,000 times faster than MGARD Q of I tuned. So if both of them are tuned, we're 1,000 times faster, which is a pretty substantial performance improvement. Lastly, we compare against systematic approaches where you essentially try all points within a configuration space to find one that works. And why is that what you have to do? We talked about the fact earlier that binary search doesn't work for these problems because they're not monotonic. Using these kind of configurations, we were able to find a solution 27 times faster on 1/4 as much hardware with a solution that was 0.5% better. So we can really start to see the benefits of using optimization to solve these problems. So to summarize this section's results, can we extend FRAS to bound simple user metrics and improve performance? Yes, and we can achieve a 56x performance improvement in doing so. We can also look at the related question, or what are the advantages of differing methods to bound user metrics? And we find that black box methods are both the fastest and the most general, but require some amount of tuning. Lastly, we'll turn our attention to understanding the effects of compression on machine learning and artificial intelligence applications. The problem that we're looking at here is that one of the biggest obstacles to the adoption of lossy compression is the lack of confidence that it is correct for a particular problem. Bounding a user's metric is a starting place, but that's usually not the ending place that users want to have confidence that it will result in a valid use. They want to understand the trade-offs that exist between different configurations of compressors for themselves relative to their applications. This is especially true in the area of machine learning and artificial intelligence. When we look at machine learning and artificial intelligence applications that use this approach, they have huge amounts of data that they often, for logistical reasons, have to compute at a different location from where they gather the data. So then this data for training needs to be transferred across the network. When we look at intersite and large bulk transfers, the literature suggests that 1 gigabyte per second is relatively reasonable. If you're looking at specialized configurations where you have a bespoke line, you can get somewhere higher, closer to 3.5 gigabytes per second. But to get faster than that, it's usually involves some kind of a stunt, something where you have unusual cooperation between all of the ISPs that are transferring the data across their networks so that they're not slowing anything down. And they're usually giving you a dedicated line to make this specific transfer. And that doesn't happen very often. And again, for network and storage resources, we find that most applications get less than 1% of the peak value available on their systems because they're sharing it with all of the other applications that exist. So dealing with these problems of storage and transfer are really important in the domain of machine learning and artificial intelligence. So the question we have here is, how can we decide what air-bounded lossy compression techniques to use in machine learning and artificial intelligence? So here I have an overview of a machine learning and artificial intelligence pipeline, beginning with receiving, training, and testing data, all the way through to evaluating the metric. We're going to take this kind of large model, an overview, and break it down into particular subcomponents and look at the design decisions that we made at each point. We'll begin with looking at the machine learning and deep learning models that we're going to evaluate for this research. In this work, we're going to look at 3 problem classes. We are interested in evaluating the effects of air-bounded lossy compression on existing applications used in the way that they currently are used, using the largest publicly available data sets that the authors have made available for the scientific applications they have under consideration. Additionally, we will use the metrics that the authors' evaluations used as their key performance indicators. We want to keep things as consistent as possible to the original domain from which the problem came, treating the problem domains kind of as controls in our scientific experiment. The data sets that we have for these applications are the largest publicly available. For Candle, that's about 4 gigabytes. For TicoDNN, which is that X-ray image reconstruction application, we have about 4 gigs of data. We have smaller buffers for 2 other problems as well. Now we're going to look at the compression and decompression piece that exists on either side of the network. In addition to the air-bounded lossy methods that we've talked about in this presentation, we also will consider sampling methods, which are used widely within machine learning and artificial intelligence, truncation-based methods, which move from a larger floating point representation to a smaller one, as well as lossless methods, which are also widely adopted in machine learning and AI. Another important question that we need to ask at this point is how to compress the data. Oftentimes, machine learning and artificial intelligence applications view their data as tabular, where each row represents an observation, and each column represents a feature or some characteristic that's shared amongst the observations. So there remains the question, do you want to compress independently by the feature, by the column, or do we want to compress related rows together? Or do we want to simply, I apologize for the people on the Zoom, compress it as a 2D data volume as a matrix, which these air-bounded lossy compressors natively understand. Lastly, we'll look at the metric that we're wanting to evaluate, and we're going to have to look a little more broadly than the metric as strictly defined by the application. So the application will have some quality metric, which we present on this cartoon on the left-hand side. On the x-axis, we have some compression ratio. So we see on this figure 3 different runs of this application representing different degrees of quality and different degrees of compression. Out of these, you would probably eliminate the leftmost point. And the reason why you would eliminate the leftmost point is there is a point to the right of it in the middle with a higher quality and a better compression ratio, so you wouldn't consider it. But you may still consider the point at the far right, which has a better compression ratio, albeit at a lower quality. Now, what I haven't told you yet is that most applications have some notion of an acceptable quality bound, some quality below which they will not accept the result. This allows us to bifurcate our search space into points to include in our analysis and points to exclude. Therefore, we would probably select the point in the center as the configuration to use for this application. When we apply this method to a collection of air-bounded lossy compression when we apply these to a variety of machine learning and artificial intelligence applications, we see this trade-off that exists between the points. One thing to note is that points in the top right corner are the best, and very clearly in the top right, we see that air-bounded lossy compression has the highest compression ratios at nearly lossless quality. Which method specifically between ZFP and SZ, which mode specifically varied between application, but air-bounded lossy compression largely was in the top right. In some cases, air-bounded lossy compression improved the quality metric over the existing kind of stable value that the application produced on its own. This is likely as a result of reduced overfitting of the machine learning techniques that are being considered. As for which method tended to perform the best, what type of airbound performed the best, we found that value range by column worked the best. And the reason for this is actually kind of interesting, that it essentially forces a different airbound on each feature. And so by bounding each feature independently, we're able to preserve quality much better than if we have one common value range relative bound for all of the points. What's interesting about this is that most air-bounded lossy compressors don't do anything like this today. They largely don't have a notion of applying different airbounds to different regions of the data. So this identifies an interesting research direction going forward for this particular problem. Results for other data sets can be found in the dissertation itself. Another problem that we tend to find in this space is this notion of an ill-conditioned problem. And on the screen, I present two cartoons which represent particular kinds of ill-conditioned problems. On the left, we have what's called a thresholding problem, where we have kind of a consistent performance of the app, and then we get to a certain airbound, and then we fall off a cliff. This is something that's particularly bad because it indicates a non-generalizability of this approach potentially to larger problems. Another problem that could exist is this idea of inconsistent effects, where we bounce from a high quality metric to a low one, and then back to a high one, and then back to a low one. And this bouncing around not only makes it hard to automatically find an airbound which produces an appropriate quality because of the noisiness of the function, but it also means that the kinds of effects introduced are not generalizable. So in our paper, we discussed two metrics for identifying these: the maximum adjacent difference. So basically, we look at adjacent points and then find the maximum difference between them, and the minimum change to sort the points as two metrics to identify these kinds of ill conditioning in the problems. A question that machine learning and artificial intelligence researchers may ask is, why not use classical methods such as the receiver operator curve, or metrics based upon it, like the area under the curve? So what are these? So the cartoon on the right indicates a family of receiver operator curves for a particular problem. And by tuning what's called the detection threshold, you can achieve different rates of false positives on your app. So a curve that goes straight up and then straight to the right, looking like an L, would be the ideal receiver operator curve, because that would be a so-called perfect classifier. However, most classifiers don't get that. They get some kind of trade-off curve that, as you adjust their sensitivity, you get kind of a set of family of trade-offs. The area under the curve simply integrates this function from 0 to 1 in order to get some estimate of this overall relationship. So why don't we use these metrics in our work? So the first answer is that they don't capture the ill-sortedness and thresholding metrics that we talked about as potential problems that can indicate lack of generalizability. Additionally, they aren't meaningfully bounded on the 0-1 interval. The airbound of a compressor doesn't necessarily produce a 0 false positive rate, even if we introduce an airbound of 0, effectively forcing a lossless compression scheme. Additionally, our comparisons that we want to consider are multidimensional. We want to consider both size and quality, not simply the sensitivity of our metric to a variety of different approaches. So now I have plotted two kind of sets of bar graphs that look at the inconsistent effects and the thresholding metrics. In the box that's currently highlighted, we have the lossless methods. What's interesting to note here is that for a certain percent loss in the quality metric, even the lossless metrics show some deviation. The reason that this occurs is because machine learning and artificial intelligence methods are non-deterministic. There's going to be some inherent variation from run to run. And because of that, we see some variance in these quality metrics that we've described. On the far right-hand side, with the worst loss in the quality metrics, we see sampling-based approaches, which are widely used in machine learning and artificial intelligence. In the middle, we see air-bounded lossy, and on the far left, we see air-bounded lossy compression, representing that it's a good middle ground between the conservatism of lossless compression and the erraticism of sampling-based methods for these problems. So what about a performance speed up as a result of using air-bounded lossy compression in machine learning and artificial intelligence applications? So using a formula that I derive in the paper, if we have a speed up on P processors for a given compressor, if that is greater than the ratio of the compression ratio times the bandwidth of the network over the bandwidth of the compressor times the compression ratio minus 1, we're able to identify a condition in which a speed up for the application occurs. And if we look at remote or IoT style use cases, what we find is that we don't even have to parallelize compression in order to achieve meaningful improvements on the performance of these applications. Within an HPC context, we only need a modest degree of parallelization, and we can actually use the automatic parallelization that we talked about at the beginning of the dissertation in order to accomplish this. So to summarize the results from this section, how do we decide what air-bounded lossy compression techniques to apply in machine learning and AI? I would argue that Pareto points, the scheme that I described for determining the optimal points, indicate that air-bounded lossy compression represents an optimal trade-off between the quality of the data that's preserved and the size. We identified a set of additional metrics that help you identify problematic use cases that weren't captured with the previous methods. We also found that value range relative compression applied by column was consistently one of the best approaches. And the reason for this is that it enforces the different air bounds on different regions. Lastly, lossy compression offers a speed up to machine learning and artificial applications with modest effort. So now I'm going to summarize the contributions that I've made over the course of my dissertation. To the design and implementation of the first unifying abstraction for scientific lossy data compression, and for automatic parallelization of compressors, I have this paper in submission to the IEEE transactions on parallel and distributed systems. For this work, which has the wrong heading, associated with the automated configuration of lossy compression, I have two papers, one published in IPDPS and another in submission to the IEEE transactions on parallel and distributed systems. And then on the area of applying auto configuration techniques to a complex application in machine learning and artificial intelligence and using tools to understand the effects of compression on machine learning and artificial intelligence training, I have this paper to be submitted to the IEEE Parallel and Distributed Processing Symposium this year. Over the course of my dissertation, I collaborated with a variety of different institutions, and 75% of the plugins that exist within LibPressio were developed in the context of these collaborations. I'd like to thank all of the scientists, graduate students, and others who have contributed to my research, specifically calling out Dr. Frank Capello, Dr. Sheng Di, Dr. Amy Apon, Dr. John Calhoun, who are here today. I'd also like to thank the various institutions that provided funding for me, including the Department of Energy Office of Science, Clemson University, the Exascale Computing Project, the National Science Foundation, and Argonne National Lab. I acknowledge funding. Here's a list of all of my papers, not just the ones related to the dissertation. And then at this time, I will take questions from the audience. Thank you for your attention.
right, very good. Thank you, Robert. That was great. So we'll start with maybe some questions from not the committee, external. We've got some people on Zoom that may have questions, or some of the audience. And actually, let me greet Robert's family here. So his mom and dad are here, and his brother and his wife, and your son, right? We're delighted to have you all here. So are there any questions from the room or from the Zoom